So to begin to understand how the electrons behave, we have to talk about the nature of light. So this is some physics again. Light is a form of electromagnetic radiation. Electromagnetic radiation is composed of two oscillating waves. One is an electric field and one is a magnetic field, and they're perpendicular to each other. So the electric field is a region in which an electrically charged particle experiences a force. A magnetic field is where a magnetized particle experiences a force. And all of these electromagnetic waves move through space at the same speed. It's a constant speed. It's known as the speed of light. It's very, very fast, 3 times 10 to the 8th meters per second. I think what the book said is that's fast enough to go around the Earth 7 times in a second. So it's really, really fast. Here's an illustration of electromagnetic radiation. So here in the red we have the electric field component, and in the blue we have the magnetic field component. So they're perpendicular. This is up and down, and the magnetic is side to side. And I have no idea why the screen is flashing like that. Light travels faster than sound. This is why when you see fireworks, you see the flash and then you hear the crack of the explosion. When we see lightning, you see the flash and then later you hear the sound of the thunder. It's because of the difference in the speed. So sound travels about 340 meters per second, light travels 3 times 10 to the 8th meters per second. And so for every mile there's about a 5-second difference in time, and that's how you can gauge how far is that thunderstorm from you. You can count how many seconds between when you see the light and when you hear the noise. Well, there are a number of ways of characterizing waves. Ways of characterizing waves. Good grief. Okay, one of them is the amplitude. So we saw that the wave was a height. I'm sorry. Oh, good grief. It's a good thing it's Thursday, which is our Friday. So the waves, they're basically sine waves. The amplitude is how tall this is. So you can have a tall wave or you can have a short wave. It's the distance from the node, and the node would be, here's 0, and it's going up and down above 0. I think there's probably a really nice drawing on the next slide. It's the distance between the node and a crest or the node and the trough. So it's the height of a wave. And that measures the intensity of the electromagnetic radiation. So if we're talking about visible light, the larger the amplitude, the brighter the light that we perceive. The wavelength is the distance between waves from one crest to another, or from this node, not to that one, but to the next one, to alternate nodes. So how long is this wave? Yeah, that's a much nicer picture. So wavelength and amplitude. The frequency, this looks a lot like a lowercase v. It's actually a nu. It's a Greek letter, and nu has a little bit of a curve on the right side instead of just 2 straight lines. Anyway, the frequency is the number of waves that pass through a particular point in a given period of time. And so it's the number of waves, or sometimes we call it the number of cycles. And so the units are cycles per second. Cycles per second, which is hertz. Now you maybe have heard of hertz. That's used, electricians use it. You have a 60 kilohertz or 50 hertz. It's cycles per second, and sometimes it's just written per second. It's whatever you're looking at. How many times does it happen per second? So 1 hertz is 1 per second. The total energy in this electromagnetic radiation is proportional to the amplitude, and to the frequency. If we think about ocean waves, have all of you been to the ocean? So if you go out and stand in the surf and the waves come in, do you experience a force when a big wave crashes over your legs? Yeah. And so that can help us to think about these sorts of waves because they behave in many of the same ways. The larger the amplitude, the more force it has. The taller the ocean wave, the more force you experience when it hits you. If it's just a small wave, you're like, that's nothing. If it's a big wave, it might knock you over. That's the amplitude. And the frequency is how frequently do those waves strike. If those waves are coming bang, 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 there is more energy in that than if you get one wave and 5 minutes later, here comes another wave. So it's related to the height, the amplitude, and to the frequency of how quickly they're coming at you. The speed at which these waves are traveling is all the same. All electromagnetic radiation travels at the speed of light. So for waves traveling at the same speed, the shorter the wavelength, the more frequently they pass, which means that wavelength and frequency are inversely proportional. So here's this relationship. The frequency is equal to the speed of light divided by the wavelength. And if we were to draw a picture, so if those two ugly-looking waves are traveling at the same speed, this one has a long wavelength, a large wavelength. This one has a short wavelength. This one, traveling at the same speed, you're going to be hit by more waves. It's going to have a higher frequency than this one. So there's some calculations that we can do. A laser dazzles the audience in a rock concert by emitting green light with a wavelength of 515 nanometers. Calculate the frequency of the light. Well, we just had an equation there, didn't we? The frequency is equal to the speed of light divided by lambda, which is the wavelength. Well, do you remember what the speed of light is? 3.00 times 10 to the 8th meters per second. And we're going to divide that by the wavelength. Well, the wavelength is 515 nanometers. Well, nanometers and meters aren't going to cancel, are they? We can convert nanometers to meters separately, or we could throw a conversion factor into our equation. Which one would you like to do? Throw it into the equation. Okay. So we're going to go in here, and we see that we have nanometers in the denominator and meters in the numerator, and we need those to go away, because frequency is per second. So we just want seconds. So I'm going to put meter on the bottom, and I'm going to put nanometer on the top, just so those units cancel out. So then we have to ask ourselves, what does nano mean? 10 to the minus ninth. So that's 1 times 10 to the minus ninth. So then on our calculator, we've got 3.00 times 10 to the 8th come on, calculator. You pick now to freak out on me. It won't turn off. Sometimes you have to abuse your calculator. Yeah. Fine. I'll use the pitiful one on my phone. Okay, 3EE8 divided by 515 times 1 divided by 1EE9 negative equals. Negative 9. Okay. I'm going to blame this on the calculator. That is not the right answer. So I'm going to work some of this. No, wait, that is, actually I think that is right. 5.83 times 10 to the 14? Okay. Yeah, I just had a little brain fart there. Should quit eating beans, I guess. 5.83, except those cause different kinds. Anyway, 5 times 10 to the 14th. And the units are, you could do it like this, per second. Or you could do it like this, per second. I've noticed from your work on lab reports, some of you are still having issues with the EE button on your calculator. It's going to come up again and again and again, and you need to get that figured out. When you enter a number like this in your calculator, it's 3EE8. It's not 3 times 10 EE8. That'll create all sorts of problems. EE stands for times 10 to them. And then you just put in the exponent. It's a shortcut. So if you're not getting the same answers as the rest of us, please ask me to talk to your calculator for you. Any questions about this one? Color. We've had some discussions about color. The color of light is determined by its wavelength. Its wavelength is related to the frequency. Frequency and wavelength are inversely proportional because the speed of light is the same. Okay, if they were traveling at different speeds, that wouldn't be the case. But they're all traveling at the same speed, so we can be thankful for that. What we perceive as white light, like what comes from the sun, is actually a mixture of all the colors of light. It's got all the different wavelengths of light. It's what we call a spectrum. And these are the colors: red, orange, yellow, green, blue, indigo, violet. And there's an order to them. If you see over here, we've got a beam of white light coming through a triangular prism, and it separates the light into different colors. And they are always in the same order: red, orange, yellow, green, blue, indigo, violet. This is why when a child draws a rainbow, you're like, I can tell that's supposed to be a rainbow, but there's something weird about it. Because they often put the colors in the wrong order, just kind of in some random order, right? One way to remember this is Roy G. Biv. So that would be like, somebody's weird name. Roy G. Biv. You can thank your parents that they didn't name you that. Red, orange, yellow, green, blue, indigo, violet. It's the order of colors. When we perceive an object as having a color, it's because that object is absorbing most of the frequencies or the wavelengths of light and reflecting the color that we see. In my phone case is red. It's absorbing the yellow light and the green light. It's reflecting the red light. The red light comes to our eyes through a complicated process. Our brain perceives that as red. Well, most of our brains perceive that as red. So, we've got amplitude and we have wavelength. So the different wavelengths correspond to different colors of light. Blue light has a short wavelength. Red light has a long wavelength. Yellow is in between. That affects the color. The amplitude has to do with how bright the light is. If it's dim light, it's going to have a small amplitude. If it's bright light, it's going to have a large amplitude. The amplitude is not connected to the wavelength or the frequency of the light. Visible light is only a very tiny part of the entire electromagnetic spectrum. The shorter wavelength light, short wavelength is going to have a high frequency, has higher energy. And that's important to be able to remember. And this is how I think of it. So here's this. I really should practice drawing sine waves. It's harder than it looks. Now these are traveling at the same speed. But which one of these looks more energetic? The bottom one, right? This one's like jumping up and down, right? Energy. Okay. Now does that really correspond to what's going on? No, but is it useful for remembering short wavelength, high energy? It works for me. This guy looks slow and lethargic, right? This is lower energy. This is higher energy. So high frequency, hitting you very, very quickly is more energy. High short wavelength is related to that. If you've got high frequency, you've got short wavelength. Okay? So within the electromagnetic spectrum, we've got a range from radio waves with the lowest energy to gamma rays, which have the highest energy. The high energy electromagnetic radiation can be very dangerous to biological tissue. It's known as ionizing radiation. It comes into your body, it forms ions, and does all kinds of horrible things to you. So here's a picture. Here is the electromagnetic spectrum. Okay, here we're looking at frequency. So at this end, we have low frequency, 10 to the 4th hertz, cycles per second. Up here, we have high frequency, 10 to the 24th. Here's the same scale, but in wavelengths of meters. So here's 10 to the 5th meters. That's 100,000 meters wavelength. It's a really long wavelength. And over here we have 10 to the minus 15th. So this is short wavelength, large frequency, because they're opposite of each other. Right here in this little tiny section in the middle is visible light. So we'll look at that first. So what they did is they took that and they blew up the scale here, because otherwise it's just way too tiny to see. So here we have red light. Red light has a long wavelength. Long wavelength, is that higher or lower energy? Lower energy. And as we go through the colors, Roy G. Biv, violet has the shortest wavelength. High energy or lower energy? Higher energy. Okay, the way this is drawn, and we always draw it the same way, from left to right is increasing energy. So Roy G. Biv goes from low energy to high energy. So outside the electromagnetic spectrum, let's first go above in energy, ultraviolet. Is ultraviolet radiation dangerous? Yeah, not horribly so, but that's what gives you a sunburn. That has more energy than visible light. We have visible light in the classroom right now, right? We can see there's light. Could we get a sunburn from these fluorescent lights? No, they don't have enough energy to damage our skin. When we go above violet to ultraviolet, that's where we're getting into more energy, and depending on your skin type, you can get a sunburn in 15 minutes, or it might take you a couple hours, right? So if we go above that, we get into X-rays. X-rays are very useful, but they can also be dangerous, right? You don't want too many X-rays. And then we get higher energy to gamma rays, and gamma radiation is very dangerous. But all of these are electromagnetic radiation. The difference is the frequency, the wavelength. Those are proportional. And it's related to energy. Yes?
We're able to see this spectrum of like not all animals can see in color, for example.
Right.
So does that have to do with sort of the physiological makeup of the shape of the eye or something, or does it have to do with the wavelengths that they can receive?
So the question is about animals and how they perceive color. I think there are some animals whose visual range extends beyond on one end or the other and is shortened. So I don't know, this is just like general things floating around in my brain, so don't quote me on this and send me hate mail. But I think it's very possible that you could have a creature who can see 700 to maybe 350. And they can't see this, just like we cannot see infrared light. But then that's because of how we see. There are rods and cones in your eyes, and those react to this electromagnetic radiation that comes in, and that causes a change in the molecules that send signals to your brain that we have learned to perceive in a certain way. And so depending on how your cones and rods are functioning, you may perceive colors in different ways. It's very, very interesting. Did that answer your question?
Yeah.
Yeah. And then if we go to lower energy, we get infrared radiation, and this is really heat. You've ever seen an infrared lamp, a heat lamp? It doesn't give off much light, does it? It gives off kind of this little bit of a reddish glow, but it generates a lot of heat. Well, it's over here into the visible spectrum a little bit, but most of what it's giving off is infrared radiation. Below that we have microwaves and radio waves. And here they've divided that up for us. Here's the radiation that your cell phone uses. Here's FM and TV. And AM radios out here. AM radio waves are the longest wavelength, and they're able to travel long distances. And that's why, like when I was growing up in Minnesota, on some evenings, we could get Texas AM radio stations. It's really kind of crazy. We didn't have internet or anything, so we thought that was cool. Okay. So, you should read about these different types of radiation. I don't think there's any point in me just standing up here and telling you what's in the book. But you should go read that. There's a little section about each of them, and you don't need to know a ton about them, but you should just be familiar with what they are, and you need to know the order in which they are in this electromagnetic spectrum. You should know that radio waves are lower energy than microwaves. You don't need to know exactly where the cutoff is, but I want you to know that order, okay? So a continuous spectrum is one that contains all the different frequencies or wavelengths. And we can use a prism to separate light by its wavelengths. And this gives us a nice rainbow. And this is what's happening when we see a rainbow in the sky. We have water droplets in the air that are acting as prisms and separating the light from the sun. This is what happens at certain times of the year in the afternoon when the light hits that chandelier just right, and it makes little rainbows all over the wall. And the kids think that's just the coolest thing ever, right? So we've seen this. Sometimes when the sprinklers are going, if you stand in the right place, you can see a rainbow in your front yard because you're at the right angle with the sun for the water droplets in the air to separate the white light containing all the wavelengths into these different colors. This is an interesting picture. This night imaging, thermal imaging. We can't see infrared radiation with our eyes, but we can build sensors and cameras that can detect infrared radiation. So what this is a picture of a guy with 3 dogs, And what we're picking up is the infrared radiation that comes off of them. And so here red is more intense radiation, and blue is less. And so we see that, yes, the dog's nose is indeed cold. So there's the dog's nose. His mouth is warm, his eyes are warm, the insides of his ears are warm. Here where his fur is very thick, we don't get much radiation coming off. Here we see the guy's bare legs, he's got shorts on, we see his face. And this is useful. You know, you can have a helicopter and fly over, and you can see warm bodies of criminals hiding in the forest, right? We can use high energy radiation to kill cancer cells. Gamma rays, X-rays, radiation in that range will damage cells. Well, we can use that to our advantage to kill cancer cells, which are reproducing out of control. The thing is, you have to figure out how to kill the cancer cell without killing all the rest of the stuff around it. One way they do that for radiation is they'll take multiple beams and focus on the tumor from different angles. And so this beam is causing a small amount of damage to the tissue that it's going through. And this beam is as well, and this beam. But they're all focusing on the same place. And so the tumor is getting this big dose of radiation, whereas the tissue around it is getting a much smaller. And there's a blurb in your book about that, which is also very interesting. I'm not going to test you on it, but chemistry is useful. It could save your life. Another thing that waves do is they interact with each other, and this is called interference. Interference can be either constructive or destructive. When the waves come together and reinforce each other, it's called constructive interference, and the wave gets larger. Destructive interference, we say they are out of phase, and they interact to cancel each other out. So here's an illustration of that. These two waves are in phase. They're traveling, they have the same wavelength, and the crest of this one is lined up with the crest of that one. When those two interact, they add together, and the amplitude of the wave gets larger. It's a sort of thing that happens, say, on a trampoline, where you get somebody jumping, and if you jump at just the right time, you can make them go a lot higher than if they were doing it by themselves. You can also have destructive interference on a trampoline, where if you jump at just the right time, the other person really doesn't go anywhere. And that's because the waves are out of phase. So here's, pointing in the wrong place. Here's the peak, the crest of one is lined up with the trough of the other. And if we add these mathematically, we end up with a straight line. They don't always cancel perfectly like that, but it will make them get smaller. So that's destructive interference, and we have constructive interference. Waves also have this phenomenon called diffraction. When a wave is traveling and encounters an obstacle or an opening in a barrier that is on the order of the size of the wavelength itself, they bend around it. Traveling particles don't do this, okay? But waves do. I'm pretty sure there's a picture coming up. The diffraction of light through two slits, separated by a distance comparable to the wavelength, can result in an interference pattern of those diffracted waves, and those interference patterns are characteristic of all light waves. Light waves do this, and waves on water do this as well. And so, you know, if you want to mess around with this at home and look at interference and things, you can take, if you've got a swimming pool, drop some drops of water into the pool and watch the ripples that come out. And as they run into each other, they will interact and they will interfere with each other, either constructively or destructively. It's a little harder to do the diffraction, One of my very fond memories of high school physics was we had these wavetables, and it was this shallow container with water, and it had a clear plastic bottom, and it had a light, and so the light shone through, and you could see the shadows of the waves on your bench. And then we had these wave generators, these little things that would move up and down, and we could put various barriers and slits, and we could make all these cool things and watch and see how the waves interacted with each other. It was just awesome. I don't actually remember a lot of stuff from high school, but I remember those wavetables. They also got a little slimy after a while, because I don't think they put any bleach or anything in them. So we started a biology experiment after a while. But this is what waves do. When a wave comes to a wall where there's an opening here, if this opening is similar in size, it doesn't have to be exactly the same size, but just on the order of the actual wavelength, when it hits here, the wave is going to be diffracted. It's going to bend. So on the wavetable, we saw straight waves coming in, and over here now we see curved waves like you would see if you dropped a rock in a pond. You would see circular waves going out like a target or a bullseye, right? That's called diffraction. Particles don't do that. When you shoot particles through a slit, the ones that hit the wall bounce off, and the ones that can get through the slit just go straight through. They do not bend. And we're going to talk about what electrons do, and so that's why I'm telling you about this. Electrons are in the realm of quantum mechanics. They can be two things at once. They can act like a particle and a wave, and so we have situations where they do both. It's really crazy. Not at the same time, but we see them do both. If we have two slits, so here's a slit and here's a slit, and here we have a light source. The light emanating from this is going out in all directions, and so this is curved. When it hits over here, there's diffraction, and it bends, and so it's like we have two new light sources. And then these are going to interfere with each other. And where the waves are out of phase is destructive interference, and it causes a dark spot on the screen. And where they are in phase, they reinforce each other and make a bright spot. And so this happens. There are some situations where something like this happens kind of by accident, where light is coming through and you'll see this weird pattern on the wall, and you're like, how are the shadows making that happen? It has to do with the wave nature of light. It acts like that, and it diffracts and interacts and interferes and does all kinds of cool stuff. So one of the things that kind of led to investigations that led to quantum mechanics was the photoelectric effect. They observed that when you shine a light on a metal, not all metals, but many of them, the metal will emit electrons. And classic wave theory would say that the light energy is being transferred to the electrons. Using classic wave theory, we would say that only the amplitude, the intensity of the light should affect the emission of the electrons. Meaning, if you shine really bright light on the metal, you should get more electrons out. And if you shine really dim light, you should get fewer out. It predicts that if you used a dim light, there would be a lag time. You'd shine the light on there, and it would take a while for the energy to build up before the electrons would come out, because they wouldn't get enough energy. They'd have to absorb energy for a while from the light before they would come out. This is an illustration of a photoelectric device. So we have an electricity source. Here we have a current meter, so we can see what's going on. We've got a positive terminal here, and this piece of metal is our negative terminal. Now, the battery here is trying to push electrons, but there's a gap. This is inside an evacuated chamber. There's no air or anything in here. And so there's no way for electrons to get from this side to the other. But what they observe is when you shine a light on the metal surface, you see current. That means that there are electrons jumping from this metal surface to the other electrode. You take the light away, the current goes away. So light shining on the metal is causing these electrons to come out. This is the basic experiment. So what they observed was that there was a threshold frequency, a minimum frequency. So if you increase the frequency of the light at these low frequencies, which are lower energy, nothing happened. No electrons. And when we got to a certain point, we got lots of electrons. There was no lag time. Just treating waves of light as waves would say that there should be a lag time. It's giving energy to the metal. After a while, there should be enough energy built up there for the electrons to come out. But that's not the case. The light has to be at a certain threshold frequency before any electrons are going to come out. The high frequency light from a dim source caused electron emission without any lag time. Now you do get a higher rate of electrons being emitted with a higher intensity light, but you still get electrons being emitted with a lower intensity light, and there's no lag time. And the wave nature of light did not explain this at all. Einstein was involved in this. He proposed that light energy was actually delivered to the atoms in that metal in packets, little packages. And those packets of light are called, a packet of light is called a quantum or a photon. The plural of quantum is quanta. Photon is photons. And so the energy of a photon of light is directly proportional to its frequency. It's then going to be inversely proportional to its wavelength. So here we have the E. E for energy is proportional to the frequency. High frequency, high energy. And there's a constant involved here, and it's called Planck's constant, and it has the value 6.626 times 10 to the minus 34 joules times seconds. You do not have to memorize that constant. But you do need to know, if you're going to use this equation, you need to know what h is. It's not the height of something, it's Planck's constant. So we've also learned that nu, the frequency, is equal to c over lambda. So we can also say that the energy of that photon is Planck's constant times c over wavelength. So these are two important equations. Let me go back to this for just a second. So this is where they started to see that light, although it definitely does behave as a wave, it also acts like a particle sometimes. And that's where this dual nature of stuff comes in. Well, let's stick with the math right now. A 100-watt light bulb radiates energy at a rate of 100 joules per second. Watt is a unit of power. Power is energy in a given amount of time. So a watt is a joule second. So 100-watt bulb, 100 joules per second. If all the light emitted has a wavelength of 525 nanometers, how many photons are emitted per second? And it says use 3 sig figs. Okay, we're going to need Planck's constant, and I can't remember it, so I'll go back here. 6.626 times 10 to the minus 34. Come on. H equals 6.626 times 10 to the minus 34. joule seconds. So what do we have here? We have 100 joules per second. We have, I'm writing way too big, we have 525 nanometers. And we want number of photons per second. I approach problems like this by looking at the units and seeing, okay, what am I going to need to do here? So photons per second, joules per second, 525 nanometers. So this light is emitting photons. The photons have this wavelength. Wavelength is related to the amount of energy. So the energy of a photon is Planck's constant times the frequency, which is equal to Planck's constant times the speed of light divided by the wavelength. Can we calculate the energy of one photon of this light? Yes, we can. Well, let's do that. So the energy of one photon is going to be Planck's constant, 6.626 times 10 to the minus 34. Joule seconds. Okay, that's not going to work. I don't have enough space. So the energy is going to be 6.626, oh, good grief, times 10 to the minus 34 joule seconds. The speed of light, 3.00 times 10 to the 8th meters per second. And then we're told that the wavelength is 525 nanometers. Let me show you kind of a, well, let's call it a chemistry hack, right? It's not really a shortcut, it's just this little trick. So 525 nanometers. But I want meters, because I've got meters per second here. What does nano mean? 10 to the minus 9th. So how about instead of writing nano, I'll just write what it means. Times 10 to the minus 9 meters. That's the same as 525 nanometers. I just wrote the full meaning of nano instead of the abbreviation. Okay. So we've got 6.626 EE negative 34 times 3 EE8 divided by 525 EE minus 9. So I'm getting the energy for one photon is 3.786 times 10 to the minus 19. Let's check our units. Meters are canceling and seconds are canceling, and so this has the unit of joules. Did you come up with that number? That's the energy of one photon. So this is, we could say that's equal to one photon. Well, we have this joules per second, and we want to know how many photons per second. So this is joules per photon, right? So we could take 100 joules per second. That's the power of the light. And we could put photons on the bottom and joules on top. And that would be wrong. I did that just to see if you're paying attention. No, I didn't. I was just being stupid. We want joules on the bottom and photons on top. That's what the units tell us to do. Because then joules will cancel and we'll end up with photons per second. See how that works? How many joules is equal to 1 photon? Well, we just figured that out. 3.786 times 10 to the minus 9. 19. Thank you. I was just like copying down that 9 up there. Okay, thank you. Oh, good grief. So that's that number I had before. No, that's not right. Okay, 100 divided by 3.786 EE 19 minus equals. It's said to assume 3 significant figures. They're telling us that because 100 watts, that's really ambiguous. So it's going to be 2.64 times 10 to the 20th. Times 10 to the 20th photons per second. Why would it be squared? This is photons. This is joules per second times photons per joule. The joules cancel, we end up with photons per second. Yeah, sorry. This is my thinking. That's not part of the... Sorry. Yeah. Yeah. But you know that there's at least one other person who was like, what on earth about the same thing? And if not in this room, then the random person who watches this on YouTube might have an issue with that. So thank you. Any questions? This is another one of those problems where you can't just plug stuff into a formula. You actually have to think about it. And you may have to use this formula and that formula and put some conversion factors in there, and you just kind of have to play with it a little bit. Think of it like a puzzle. Okay, it's not going to be obvious. You're going to have to think about it. Wow, this is a long section. Okay. Ejected electrons. So let's think about those electrons that get ejected from the metal. 1 photon at that threshold frequency has just enough energy to dislodge a single electron from the metal. If you've got a photon that's below the threshold frequency, it can't eject any electrons. So you get right up to that threshold frequency, and that photon has enough energy to eject 1 electron. And so what is holding those electrons in there? Well, I think this is phi. We use this Greek letter to represent the binding energy of an electron. The electron is stuck in the metal with a certain amount of energy. And in order to dislodge it, you have to hit it with enough energy to kick it out. That energy is actually measurable, and it's phi. If we irradiate that metal with higher frequency photons, the electron is going to absorb more energy than is necessary to escape. The excess energy becomes kinetic energy. So the kinetic energy of the electrons that get kicked out of the metal is equal to the the energy of the photon minus the energy that was binding the electron. Does that make sense? No? Okay, I'll try it again. Well, does that work? Okay, I'm trying to think of a kind of a real life analogy, and this one is just kind of formulating, and I don't know if it's a good one, but I don't have time to think, so I'm going to go with it. Okay, so guy's in jail, and his bail, he didn't do anything horrible. His bail's $500. So you come in to bail him out, and you have $400. Are they going to let him out? No. You come in, you have $500. They going to let him out? That's his bail, $500. He comes out, now he doesn't have any money, but he's out of jail. So what if you go in there with $1,000? You bail him out, and then he could have the rest of that money. So he's taking off now. He got bailed out for the $500, and what's left is $500 that he's leaving with. It's not a great analogy. So here we have the electron. This is the energy of the photon is you coming in with a certain amount of money. The energy that's binding is like his bail amount. Okay? So if you come in with exactly the amount for his bail, he's going to get out, but he's not going to have any energy left. If the photon comes in with more energy than is needed to get him out of jail, he gets that energy as kinetic energy. So if the photon comes in and is just way too big, a little bit of that energy gets used to eject the electron. Where does the rest of the energy go? It goes into the kinetic energy of the electron. Is that any better? Good. Okay. It's one of those things that once you see it, it's just not that hard. But the seeing it the first time is really the hard part. So the kinetic energy of the electron is the energy of the photon minus the energy that was binding it. This energy is expended in removing the electron from the metal surface. And so whatever's left from the photon's energy is what he has as kinetic energy. Well, the energy of the photon is h nu. Planck's constant times the frequency. And the binding energy is what gets subtracted off. So the kinetic energy is equal to h nu minus 5. Example. This one thankfully doesn't have any numbers. Suppose a metal will eject electrons from its surface when struck by yellow light. What will happen if the surface is struck with ultraviolet light? Okay, so first we have to figure out, is ultraviolet light more energetic or less energetic than yellow light? It's more. So how can we remember that? Roy G. Biv. Okay, so this end is high energy. And think about sunburns if you need to. Ultraviolet is after violet. That will give you a sunburn. And this end is low energy. So it takes at least yellow light to kick out electrons. What will happen if it's struck with ultraviolet? Well, ultraviolet is up here. It's got more energy. So will it be A, no electrons? No. The electrons are ejected, and they're going to have the same kinetic energy as those ejected by yellow light. No. They're going to be ejected, and they have greater energy. Yes. Let's at least think about that last one. Electrons would be ejected, and they would have lower kinetic energy than those ejected by yellow light. No, that's not true. So here we've got photons of ultraviolet light, more energy than what is needed as a minimum. Yellow light's the minimum. The energy of the yellow light is that binding energy of the electron. So when we use a photon that has more energy, the electrons come off and they have kinetic energy. What if we used blue light? Would we get electrons being ejected? How would their kinetic energy compare to those from the ultraviolet light? Less energy. Okay? So this sort of a question, you should be able to think about it this way, really more in a conceptual way than necessarily in a mathematical way. But sometimes we just have to see the math before we can understand the concept. Okay, wave-particle duality of light. Sometimes light behaves like a wave. We see it interacting with prisms and diffracting and doing all these things that waves do. But at other times, light acts like a particle. The photoelectric effect is light acting like a particle. Light acting like a wave does not explain what happens with those electrons getting kicked out. So which behavior you observe depends on the particular experiment. And this is part of that superposition thing. That light is a particle and a wave until you observe it. And then it has to be one or the other. It can't be both at the same time. And on that note,